We're now going to examine a feature that all continuous functions have, and it's outlined in our what I call our first valuable theorem. I call it that because it has the word value in it. It's called the intermediate value theorem. And I'd like to demonstrate the principle first with an idea that we use almost every day, the idea of driving in a car and looking at the speedometer. And so I actually would like you to just read the scenario that's presented here, read the table, and then think about the question that's on here. The question at the end is, did the speedometer's car ever read exactly 52 miles an hour? If so, how many times? I'd like really to say, what's the minimum number of times? I'd like you to maybe pause the video now and look at this question in the table and think about how you would answer the question. Well, hopefully you took a look at this and you maybe hopefully found that you think it might have happened at least 2 times. If you've ever driven in a car and you've accelerated it, then for example, you might have noticed something like this, that in this first 5 seconds, when the speed or velocity increased from 0, maybe when it was stopped, and 5 seconds later the speedometer read 20 miles an hour, we know that at some point during those 5 seconds, it would make sense to me that at least that at some point during those 5 seconds, the speedometer would have read 12. Because how can you accelerate from 0 miles per hour to 20 without at some point going 12 miles an hour? So since this one's looking for 52, you hopefully were looking for a sub-time interval within this table where maybe at one point the speed was below 52, and then the very next time you read it, it was above 52. And you would know then it read 52 somewhere within that time interval. And I see that happening right here. I'm circling it. It's the time interval that went from 15 seconds to 20. And then at the same time, the car slowed down from a speed of 60 to a speed of 50 in this 5-second time interval. So we can predict that sometime during this 5 seconds, as it slowed down, it was going 50. Now, we know this is true because if you've ever ridden in a car or driven a car and looked at the speedometer doesn't suddenly change like this. It has to gradually change and continuously change. So the graph of this, as the car sped up and then got to about 60 and then gradually slowed down again, we know if we were to plot the velocity more frequently, we could plot it maybe even so often that the graph would be continuous. Even though we might only be able to plot a few of them here, the drawing of the velocity graph really is a continuous function. So if at one point the speed was 50, let's say, and another time the speed was 60, then for sure somewhere in between is a time when it was 52. Okay, just because this graph must be continuous, and therefore you can't go from 50 miles an hour to 60 miles an hour without having been 52 somewhere on the way up there. Okay, and so the terminology we give to this is there is a time interval. Okay, like in this one here, it was 15 to 20, so maybe between 15 seconds and 20 seconds, the speed went from 50 to 55. Okay, so we'll highlight maybe 50 miles an hour, and then 55. So if some part in there is 52, I had to have hit it. Okay, so we call 52 an intermediate value between the value of the function at the beginning of a time interval and the value of the function at the end of the time interval. It is an intermediate value, and because the function is continuous, it's going to have to hit every intermediate value. And that essentially is what the theorem is about. So remember, the function this principle requires that the function be continuous, so we won't be permitted to jump over any holes. And it says, if I study this function on a particular interval, the interval is notated a comma b, so there's a starting value a, and an ending value b, and that creates an interval on the x-axis, and is assuming that the height of the function at a is different than the function value at b. So f of a and f of b are different, and it's notated here that they're different. Then it says for any value between f of a and f of b, and we're going to call that k. So for any number k that is in between those, I'm guaranteed that I can find at least one point within this x interval that I'm going to hit it. Okay, so in the problem about the vehicle and the speedometer, there was, for example, one interval where at the beginning the speed was 60, and then at the end the speed was 50, and an arbitrary intermediate number was 52, and I guarantee that I'm going to hit 52 at least once. If the graph were to just be kind of straight and only just connect these 2 points, I would have to hit it once. If it bends a few times like this one is, I could hit it more than once. So the theorem only says I'm guaranteed at least once. Okay, so it doesn't promise anything above that, but we're guaranteed to have at least one. So we're going to demonstrate this, and actually in a couple examples find that number c that's within a given interval. And so again, you notice here, if the continuity were removed from this theorem, it's possible this might not work, right? So in this case, f of a is different than f of b, but because the graph has a discontinuity in it, I might be able to find an intermediate value that I don't ever hit. So we're going to use this as our example. It says determine if the intermediate value theorem can be applied, and then if it does, let's find the values of c guaranteed by the theorem. Reading the theorem again, it says if a function is continuous, and we can make a note of that. We do know that f is continuous. It's a polynomial. Okay, so usually it's good just to be familiar with common functions and know that they are continuous all the time. And this is. Okay? And then the second part says if the function valued at the left end and the function valued at the right end are different, and so we're going to now do that. We're going to find f of -3, and we're going to find f of -1. I encourage you to pause the video maybe at this point and see what those are. And I'm going to evaluate them now too. So taking -3, this would be x squared would be 9. 7 times -3 is -21, and then plus 5, and if I take 9 plus 5 and get 14, and then 14 minus 21 is going to give me a result of -7. Taking -1 squared first is going to be 1. 7 times -1 is -7, and then plus 5. So noting now that I have 1 minus 7, which would be -6, and -6 plus 5 is -1. Now I arbitrarily gave you a number here, -5. We're going to try and see, is it guaranteed that the function will equal -5 somewhere within this interval? The reason it's going to is because -5 is between, it's less than -1, but it's greater than -7. It's between the two values of the function, one at the left and the right. So I guarantee there will be some place between -3 and -1 that the function equals -5. So to go find it, we just have to set the function equal to -5. X squared plus 7x plus 5 equals, sorry, not 0, equals -5. And I encourage you to pause the video now and try and solve this yourself. It's one I think you should be able to solve with algebra, but I will solve it in a minute. So if I were to solve it from here, I would want to get this quadratic in standard form by adding 5 to both sides. It would now make x squared plus 7x plus 10 equals 0. You should now attempt to try and factor it. Now, if it didn't factor, you could use the quadratic formula, but I'm going to factor this down, x plus 5 times x plus 2. And I'm going to get the solutions x equals -5 and x equals -2. Now make note, this problem involved the interval -3 to -1. So this theorem only guarantees I'm going to find at least one solution that's between -3 and -1. So the only relevant solution down here is -2. The other one is a solution. It makes this -5, when plugged into the function, is going to make the output -5, but I don't really care about that one because it is not within the given interval.